So on page 4 of section 7.4, and again we're calling this 7.4 most because we are covering most of the material in 7.4 right now. We'll come back for some leftovers a little bit later. We're focusing just on the part of the special two-term formulas here. And page 442 reminds you of the sum or difference of two cubes here. And again, they use the SOAP, same signs, opposite signs. They don't include that always plus part, which helps you get the SOAP. But this one is always plus. So it always matches the formula of SOAP, S-O-A-P, in terms of the signs. In terms of the letters, you get an A, your B, your A squared, your AB, and your B squared. So it's one pattern gives you two formulas. Okay? And then on page 443, remember how we suggested to get familiar with so you could recognize the perfect squares. Here's your chance to recognize the cubes. And they go from 1 to 10 here. These are your most often used cubes. So, and they, well, I'm sorry, 1 through 6 and then 10. If you wanted to, you could also look at 7 cubed, 8 cubed, 9 cubed, but those are not going to be as prevalent in some of these. If you can get familiar with 1, 8, 27, 64, 125, and 216, recognize that those are perfect cubes. When you see them, you can save yourself precious minutes on an exam. Better make sure that we can see this. Let's move down just a little bit. Okay, so if you want, you can get your 7 cubed memorized, which is 343, your 8 cubed memorized, which is 512, and your 9 cubed memorized, which is 729. But again, you'll even maybe hear that I'm clicking on my calculator here just to come up with these. These are not as necessary, not as common when you're looking at some of the problems. If you focus on the 1 through 6 cubed and the 10 cubed, recognize these numbers here on the left. When you see them, hey, that's a perfect cube. Now I know I'm dealing with sum of cubes or differences of cubes. The one to watch out for is that 4 cubed equals 64, because 64 is a perfect square, 8 times 8, and 64 is a perfect cube, 4 times 4 times 4. So use your other piece to determine if it's a perfect, if it's being used as a perfect square or perfect cube. Okay, and then here they do help you on the study tip next to that with the SOAP, the always plus. So I jumped to conclusion a little bit. They were just showing the pattern here, and then they finally do let you in on the SOAP thing. So let's finish this page with the application exercise underneath. You can expect that while we're in this section, the application exercise would ask you to then at some point utilize factoring with one of the special forms. So let's see what that looks like here. It says find the formula for the area of the shaded region and express it in factored form. And very similar to what we did in Math 60 and what we started to do at the beginning of Math 65, you're going to have to sometimes bring your own formula, bring your own knowledge to the situation. In this case, when we're finding area of a rectangular region, it's going to be length times width. Okay? And the other thing you want to note here is that they're asking you to express your formula in factored form. So you get to practice factoring here. So let's look at what they're talking about. The area of the shaded region. So shaded, and mine is just a little skewed here, this copy. Sorry about that. But it is 2 rectangles based on the 90-degree angles that are marked here in the corners. The shaded area is going to be represented by the big rectangle minus the small rectangle. So this kind of purpley looking shaded area is found by taking the area of the big rectangle. Maybe we should be very clear. Area of the big rectangle minus the area of the small rectangle. So in this case, the big rectangle has a length times width of 3x times 3x. And the small rectangle has a length times width of 2 times 2. what you get then is, when you multiply that out, 3x times 3x is 9x squared, minus 2 times 2 is 4. That's an expression for the area. But then we're going to practice factoring it, okay? So now factor. And the reason why we factor is because the directions told us to, okay? We're not going to get into right now, how do you know if you're supposed to factor or not? That's for later when we're applying this and we're solving equations. That's for near the end of chapter 7. For now, we're going to get good at factoring. They're going to tell us when to do it, okay? So in this case, and we can see it one step above, this is a perfect square, but first we need to check, is there a GCF? Is there anything that both pieces have in common? No. So next, how many terms? Again, shouldn't be a shocker while we're in this section on special formulas that there's 2 terms. So we are dealing with either a difference of squares, difference of cubes, sum of cubes, because there is no formula for sum of squares. So it is a difference, so it's going to be either the difference of squares or difference of cubes. And it turns out to be a difference of squares because this is going to be 3x times 3x, and this is going to be 2 times 2. So our 3x is our a value, our 2 is our b value, our formula is a squared minus b squared is equal to a plus b, a minus b. I'm seeing and hearing and writing and saying the formula for it every time I use it, gets it into my long-term memory. So in this case, our factored version is the 3x and the 2, our a values and our b values, and we make 1 plus and 1 minus, and then we're done. And that is our factored form. And there were no review and preview exercises this time around. We'll catch those when we hit the leftover chunk of 7.4. So a little bit of a break on the problem set there.